some knowledge of a K value, which is an equilibrium constant. That equilibrium constant is temperature dependent. So at any given temperature, a reaction has an equilibrium constant. If you change the temperature, you change the equilibrium constant. I just want that to be very clear. The equilibrium constant tells you where the equilibrium lies and how much it lies there. So if we're talking about a reaction that has reactants in equilibrium with its products, if K is greater than 1, it lies to the right. You have more product at equilibrium. And the bigger it is, the larger that ratio of product to reactant is. Big K values tell you that you have a lot of product and a little bit of reactant. An equilibrium constant that's equal to 1 means that your products and reactants are equal. That doesn't happen very often. If K is less than 1, at equilibrium you have more reactant. It lies to the left. You haven't shifted very far to the right. Or you did shift to the right, but you shifted back to the left again. It pushed to the right, you made some products, but then in the end, when the rate of the forward equals the rate of the reverse, you had more reactant than product.
Okay.
And if you have more reactant than product, the smaller this K value is, the more reactant to product ratio you have. Okay? Questions so far? All right. We then can use something called ice tables with our reaction, where we put the initial amounts, how much it changes, which will be based on the coefficients, and then use that to find our equilibrium amounts, or to find K or whatever.
What does I stand for again?
Initial change equilibrium. I was going to say something. Oh, in a K equation, yesterday we learned that it could be molarities. That would be a Kc. We're going to start making a list of Ks. Kc is when you put molarities into your K equation.
Why is it K?
Equilibrium constant K. Somebody picked it. I don't know why. Plain old K, you could use moles of stuff, whether it's aqueous or gas. Molarity is moles per liter for aqueous solutions.
Right.
Moles is just amount. This could be aqueous or gas. Solids and liquids, we're not going to include in our K equations. Can't do it. They just get left out. Because in a solid or a liquid, for equilibrium, you're not going to see a change in those they just don't change very much. They kind of stay whole, minus just a tiny bit. So we're not going to see those. Only aqueous and gas.
Why can you use molarity for solid ways for
Just depending on what you're given. If you're not given volume, we're going to assume that in the end, the volume would be the same anyway. So you're going to divide everything by that same volume. And moles will work.
Oh, because okay, that makes sense.
It's dividing everything by the same number anyway. So
But if they don't give you volume, how do you do that?
you just use moles. But if they give you molarity, you can use that without having to worry about it.
So if they give you molarity, does that mean that the volume is changing?
Not necessarily. It just means that you don't have to do anything with the volume. You could be given moles, put that in your K equation. You could be given molarity and put that in your K equation. You might not be ever given volume, just given molarity or moles.
Okay, now I'm really lost.
We're going to do examples. You'll get it. I promise. Okay, so let's look.
Can the recording hear us? And all my not smart buttons.
Do what?
Can people in the recording hear me?
No, probably not.
Okay, cool.
All right, another ester, ethyl ethanoate, can be formed by the reaction of ethene with ethanoic acid in an inert solvent according to the equation C2H4 plus CH3COOH makes ethyl ethanoate. In one experiment, 0.5 moles of ethene were allowed to react with 0.25 moles of ethanoic acid, and the total volume of the mixture made up to 500 milliliters with an inert solvent. When equilibrium had been established, the mixture was found to contain 0.220 moles of the ester. Calculate the molar concentration of all three substances present at equilibrium, and hence the value of Kc. Okay, so this is where if you're asked specifically for Kc, you have to use molarity. If you're just asked in general for K, you can use moles. Okay, so Kc is specifically, the C stands for concentration, and concentration means molarity. Okay, so this is where we're all going to start seeing where and when we have to do moles or molarity. I'm going to rewrite the reaction so you can see it. C2H4 plus CH3COOH.
Why can't we just write OT?
It's trying to show you where the bonds are. Initial change equilibrium. And then I have point for ethene, which is C2H4. I have 0.5 moles divided by 0.5 liters. So it's 1 molar ethene to begin with. And my ethanoic acid is another word for acetic acid, which is vinegar. We have 0.25 moles divided by 0.5 liters. So 0.5 molar. Those are our initial concentrations of our reactants. So we can put those in here. 1 molar C2H4, 0.5 molar CH3COOH. And initially, how much product do we start with?
Is that the liters?
How much product do we start with initially? Do you start with product?
Oh, no.
No. Okay, and then they give us more information. They tell us when equilibrium has been established, the mixture contained 0.220 moles of the ester. So this is initial. At equilibrium, we have CH3COO C2H5. We have 0.220 moles, and we still have the same volume. Volume is conserved. 0.5 liters. So what is that?
Why isn't it 1 liter? Because when if you added...
It was diluted to a total of 500 milliliters.
Oh.
.44 molar. that is my equilibrium amount of this. Are y'all with me?
Mm-hmm.
At this point, I've just filled in everything that was given in the problem. I was told these are my initial concentrations, and this is my final concentration. I filled in everything I could on my ice table. Then, once you know everything in the ice table, you need to figure out what is your change. The change is usually going to be a variable to begin with. I'm going to lose some amount of reactant, X. And it's a 1-to-1 ratio. So if I lose X of this, I lose X of this. Right? And it's a 1-to-1-to-1 ratio. So if I lose X of these, I gain X of that. Reactant going to product.
Why would you gain 2x? Because you're subtracting 2x.
It's still mole-to-mole ratios. For every 1 mole of this, I have 1 mole of this. For every 1 mole of this, I have 1 mole of this.
But that's 2 moles.
That's you can't think of it like a mathematical equation in that sense, where you lose 2x and you gain 2x. If you lose X of this, you gain X of this. The only way I would put a 2 here is if there was a 2 out here to balance it.
Like, is it like if everything in there is in parentheses and there's a 1 on the side?
Kind of, yeah. Okay, so now 0 plus X equals 0.44 molar. So what's X? 0.44 molar. One minus 0.44 is 0.56 molar. 0.5 minus 0.44 is 0.06 molar. And then 0.44. So now, to calculate Kc, I take the concentration of the product divided by the concentration of the reactants and I get a Kc value of 13.1. No units on Ks.
How did you know you had to divide the product by the reactants?
You remember from the video yesterday, all Ks, like if you have AA plus BB in equilibrium with this, the general form for K is always
Oh, yeah.
C to the C, so that's where I got that. I'm going to finish this just so it's not confusing.
Is that big C to the little c?
Mm-hmm. Big D to the little d, big A to the little a, big B.
So if one of those things had a, like if...
Pretend it had a 2 here.
Yeah, would that mean it's squared?
I would have squared this.
Oh,
But that also would have made this a 2x.
yes. So then if they're all, like if you do make that 2, the other 2 would have to be 2. That wouldn't work. But then you'd square all of them.
No, you would only square them if they had 2's in front of them.
Yeah.
But yeah. Yep. Alicia?
So like for this whole table, if you're not doing it with Kc and you're just doing it with K, then you could do all of this with moles instead of
Moles would have been fine.
Okay.
And honestly, you might notice that we would have gotten the same answer because I divided all those things by 0.5.
So why do we have to divide them?
Because right now, I want you to understand that Kc means concentration, because on the AP test, they might not ask you to finish this, like they might ask you to go that far for Kc and just plug in molarities, and you would get credit for just filling in numbers. And it has, for Kc, it has to be molarity because it means concentration. So we're just going to practice that way. I understand you get the same answer if you're just calculating K, but sometimes they just ask you to write the expression, and you need to know, okay?
So on our test, we don't divide everything by, if it's like a really weird number and it's going to make a really long decimal, are you going to take off points if we
I wouldn't take off points if I asked you for K, but
Okay.
if I asked you for KC, I would. You have to know the difference.
Oh, okay. Alright. So I would forget that information.
Okay. Question so far. This is actually for those of us, me, you, some of you, if you are a person who is a very organized note taker, math person, ICE tables are actually useful. You are going to start liking these. I use these sometimes for really hard limiting reactant problems. It helps you just keep track of what you have and what you're missing and all that stuff. Questions? Okay. The other type of K is KP. And this is based on partial pressure. These have to be gases.
What is, oh, you said liquids.
To find a partial pressure, which is PP, and let's say you have PP of A, you take the mole fraction of A times the pressure total, the total pressure. And if you remember, mole fraction is moles of A divided by total moles present. So for the same equation, Kp would be the partial pressure of C to the C, the partial pressure of D to the D, divided by the partial pressure of A to the A, and partial pressure of B to the B.
I thought partial pressure was just all the pressures added up, but like it's the one pressure.
I mean, yes, same thing. It'll work if you're given that, but you're not going to be given that. You're going to be given total pressure in mole fractions.
Okay.
Either way works, though. Okay, so this is important. Students miss points on this every single stinking year. If you are asked to write a KC expression, not even with numbers, just with equations, like just chemical formulas, if you put your things in parentheses instead of brackets, they do not give you the point. Because brackets means concentration. KCs require brackets. Inversely, for a KP equation, if you're asked for that, if you use brackets, you do not get the point. You have to use parentheses. Here's how you're going to remember it. KP, use parentheses. P requires parentheses. and then C requires brackets. Just get in the habit, even if you're using numbers, even if it wouldn't matter, anytime you write a KC equation, use brackets. Anytime you write a KP equation, use parentheses. And I know, when I was in college and now if I do problems, I don't even pay attention. I just use whatever. Because when you're just getting an answer, it really and truly doesn't matter what you use. Mathematically, we know brackets and parentheses mean the same thing. Chemically, brackets means concentration. It stands for something. So if you put brackets in a KP equation, in chemistry terms, that's very confusing. So don't do it. Okay? Just get in the habit. C's brackets, P's parentheses. Okay. That's all for today. No, let's do an example. I'm going to do this one example. Dinitrogen tetroxide dissociates into nitrogen dioxide. Initial change equilibrium. Okay, so when we're doing KPs, if you're not given partial pressures right off the bat, my suggestion to you is put mole values into your ICE table, and then when you're done, convert those mole values into partial pressures to put in your KP equation. That will make your life easier. Okay, so initially we have 1 mole of N2O4, and initially we rarely have any product. Unless you're told explicitly, you start with product. Most of the time, this is going to be a 0 initially. Good? Okay. Change minus x plus 2x. Y'all with me? Okay, and then it tells you it's 45% dissociated. What does that mean if 45% of it went away? How much do I have at equilibrium? 65%. And 65% of 1 is 0.65. Right?
Yes.
It's 45% dissociated, which means you have 65% left. 55.
Oh,
Math.
that was so.
Sometimes I'm not able to do math.
I did
0.55. Okay. So, 1 minus 0.45 gave me 0.55. That means x is 0.45. So, plus 2 times 0.45 is 0.90 moles. Does everybody agree with that? Did I do the math correctly this time? So these are my mole values at equilibrium. I'm also given a total pressure of 3 atmospheres. So I'm going to find mole fractions. My mole fraction of N2O4 is 0.55 moles divided by 1.45 moles, which is not something I can be trusted to do today. 0.38. And then my mole fraction of NO2 none. 0.9 divided by 1.45 is 0.62. And then I need to find the partial pressure of N2O4 by taking 0.38 times the total pressure, which is 1.14 atmospheres, and then 0.62 times 1.14 atmospheres is 0.71 atmospheres.
So that number is just from dividing by 3?
Multiplying by 3.
Oh.
I'm finding like the part of the pressure. And then Kp is going to be the partial pressure of NO2 squared, so 0.71 atmospheres squared. See how I use parentheses because it's Kp, divided by the partial pressure of N2O4, which is 1.14. And I get a Kp value of 0.44. Alicia?
Why did you divide the mole? Where did you get this number and why did you do it?
I needed the mole fraction to find the partial pressure.
What is the mole fraction?
The mole fraction is the part divided by all the moles. So at equilibrium, I have 1.45 moles and then 0.55 divided by that.
Okay.
It's kind of like a percent without making it a percent. It's the decimal. So that you can find what part of the pressure is that gas.
Can you write it as a percent? That makes no sense.
I mean, you can, but then you're going to have to go back and use it as a decimal anyway.
Wait, so are the partial pressures going to add up to be 100%?
It should.
Okay.
Okay. And then part B says, what will be the percent dissociation of nitrogen tetroxide at the same temperature, but at a total pressure of 1.5 atmospheres? So at this point, you would have to go back here and change your partial pressures by,
Did you just multiply by 1.5 instead of 3?
you would have to go all the way back to X. But I'm going to do that example on the video tomorrow.
What?
Sorry.
Why?
Because I'm only
No.
seeing part of students.
Why do you have to go back to X? We didn't even use 3 atmospheres until we got to the end.
Right.
Are you gonna have to divide everything by 2?
But see, if we're trying to find if it's a different percent dissociation, so we'd have to go all the way back here and figure out what X is. We'd have to work backwards. But is it going to be different?
Why would it be different?
I'm asking you.
I don't know.
It wouldn't be different. But I was going to go over that tomorrow.
Oh.
So you're right. Yes, I didn't use 3 atmospheres until all the way down here. And they're asking me, is it going to change X? No, it's not. Because everything's going to be multiplied by that same number, and it's all going to cancel out. It would have no effect.
Yeah.
Okay.